Hello everyone, welcome to the control system. This is part 6 of lecture 6 on state space representation, and we will continue from the previous section on numerical integrations in MATLAB. This is another example. Uh, Basically, there is two uh, card number 1 with mass m1, card 2 with mass m2, and card 1 is connected to card 2 by a spring and a damper, and card 2 is connected to the wall by the spring and the dampers. Card 1 has the displacement pt and card 2 has the displacement qt. Okay, so this is a free body diagram of mass m2 and mass m1. I think you already know how to do all of this using Newton's second law. So this is the equations of motions of the card number 1 and card number 2. And in this case, you can use the same procedures as we have discussed so far. So I'm not gonna explain you how to derive it again. If you don't remember, you can go back to the previous section and then try to review everything again. Okay, this is the state space representations. So we choose x1 is p and x2 q, and x3 is the derivative of p, and x4 is the derivative of q. Okay, so uh, this order doesn't matter. You can choose uh, p dot q, or q dot is also fine. But in this case, I would just choose this. Okay, so and then finally you obtain A and B and C. So D is 0. Okay, so it is a 4 by A is a 4 by 4 matrix. B is a 4 by 1 matrix. C is 1 by 4 matrix. So suppose that the two rolling cars have the following parameter values. Okay, so K1, K2, B1, B2, and M1 and M2, with the initial condition P0 equal 10. This should be 10 meters, okay? Not 10 centimeters. Q0 equals 0, P dot 0 equal Q dot 0 equals 0, and there is no input driving force. So that is U0 equal to 0. So in this section, we focus on numerical integrations. So let's do it now. Okay, based on the equations. So this is MATLAB, and we have to do the same as we did before. Okay, so I create a folder called code demo2, and I create one main file. All right, main files using ODE45 as we did before, and I need to specify the model, the t-spans. T-span is the time interval that we want to integrate. X0 is the initial condition, and this model is the state space model. Okay, and you have to write the MATLAB functions. So in this case, I wrote MATLAB functions given by this model.m. So as we did before, dx is the output of this function, and with the function name model, the input t, and the state x. Okay, and then I need to specify the parameters, the constant parameters. So we have the spring coefficient, damping coefficient, and mass m1 and m2. And in this example, we assume that the input pulse u is is 0. Okay? And we need to specify A, B, matrix A and matrix B, and then finally dx equal A times x plus BU. Okay? So, and after that, you can plot it. Okay? So this is a function to plot the figures from this to this. Let's run the code. Alright, so this is uh, the trajectory of the state. So in this case, I only plot not all the state. I only plot P and Q. Okay, so this is the displacement P, and this is the displacement Q. So after a period of time, you can see that it is die out. So it go to 0 because of the damping coefficient. So we have the dampers in the system. Okay, you can plot it. Let's say 10 seconds. Okay, and you can view the result. You can see after a period of time, it just die out, both P and Q. For example, if you want to change the damping coefficient, let's say this is a damping coefficient. Control C. And I'll comment this out. And change it to 0. So there is no damping and no damper. Save, run it. Where is it? It's in the back. See, it keeps oscillating. So it keeps oscillating because we set the damper to 0. So let's keep the damper the same. You just need to uncomment this. Okay. And you can also change the input force if you wanna. In this case, U is 0. You can change it to sine t. It's also possible. See. Okay. So this is the end of this part. If you have any question on this section, you can drop your comment in the group chat. Thank you.